Right. Thanks everybody for coming back for the third week. We're very excited and we're going to be very brief because we have 4 readouts from the previous sessions. So first, thank you again for all of your hard work so far. A couple things to expect. We're going to have working drafts of the workshop section reports. This will be for each session that we've had. These report templates are sitting in your folders. There was a couple that weren't there. I believe I got all of that fixed this morning. And this is what their names look like. So hopefully you can see there is a common theme to how we named them. And feel free to get started on those. We would like the first sessions. This is kind of the first due date today and tomorrow. We'd like those to get out so that we can have people just make some comments and we can start reading them and seeing where it's going and find out if there's anything that we need to do in addition to the workshop to gather information and that sort of thing to actually get to where we need to go. The other good news is from the confirmed participants that have filled out the Google form, we had 186 unique institutions represented from across the world. So I was excited about that and I wanted to share it. That's all I have for those logistics. I'll quit sharing my screen and we can go to our readouts. And who is up first? Let's see here. And jump in. Who do we have? Christa, do you want to go first? I guess we don't technically have to go in any order. And if Krista's not online yet, we can.
I just got a message from Christa. I'll help her get on.
Okay, in that case, Char, are you on? And would you mind going?
I'm going to be doing the hydrology one. This is Scott Peter.
Scott, great. Thank you. If you don't mind going, that would be wonderful.
Sure. All right, can you see that? Yeah, so I will be reporting out for the organizers shown here. We had 3 talks in our hydrology session. The section leads gave an introduction and sort of an overview of the state of the art. We had Greg Nearing talking about stream flow simulation. Alex San talking about some of his work. We've also had 2 hydrologists in plenary sessions. Xiaoping Shen talked last week, and then Allison Appling will talk next week. We divided up into 7 breakout sessions. They're listed here. Obviously, there's quite a bit of overlap between those. For example, you can't really understand soil moisture without understanding evapotranspiration, or you can't understand groundwater without understanding human impacts. But for them, still this is a kind of was a reasonable way I thought to organize the material. Let's see. We gave the participants guidance that everyone got, but in addition to that, we thought it was important to provide some additional guidance that's very specific to hydrology. Hydrology is somewhat different from some of the other topics because it is both an engineering field, an applied field, and a fundamental science field that is sort of foundational for understanding the Earth system, and both at present and how it will evolve. And so it's important to make the distinction between those 2 classes of hydrology applications. A lot of machine learning has been done in hydrology, but almost all of it, or the vast majority, I would say, is really more in the engineering focus hydrology application. And that's fundamentally different than trying to understand, hydrology in the context of the Earth system. So we reminded, what DOE Office of Science interests were in this topic, more focused on the Earth system and decadal projections and process understanding. Each of the breakout sessions came up with several grand challenges. I won't list them all, but we tried to look at them and kind of come up with some high-level views. And these may be kind of obvious, but we have specificity for each of the breakout sessions. So we're, combining machine learning and process models to improve model projections. That would include, removing biases, reducing uncertainty, improving spatial and temporal resolution, and especially really the representation of extreme events are quite challenging, which maybe machine learning can help combine with process models. Related to that, but maybe different, is using machine learning to combine diverse data sources to get better data products for model input or for model evaluation or for just for evaluating to develop that basic understanding that we need. And finally, one of the challenges that we see is using data-driven machine learning representations for components of the hydrological system that are we really don't have reliable process representations for. An obvious one is the intervention, human intervention in the water cycle. But there are others. For example, preferential flow in the Beta zone has traditionally been a challenge for hydrologists, and we may see some progress there with machine learning. Potential next steps. Several of this breakout sessions talked about the need for tools or perhaps some sort of data clearinghouses that make it easier to combine multiple data sources that really haven't been looked at before. That can be done now, but it's pretty labor intensive, and there may be some benefit in developing those tools. An abstraction layer, if you will, that can really look at multiple data sources and allow us to experiment with combining those. Expanding sort of standardized data sets. The CAMELS data set has been really valuable for advancing machine learning for a particular applications, which is streamflow simulation. So having those standardized data sets for other parts of the water cycle could be very valuable. We see also a potential for developing software frameworks that make it easier to explore different combinations of machine learning and process-based models. We can do that now at a coarse-grained level, but we think there's a lot of benefit in developing the tools that allow us to look at that at a more fine-grained level. And finally, there was a lot of discussion about the need to, to have people who are both knowledgeable about the domain science as well as the machine learning algorithms. And there's a potential here for, providing some sort of path forward for workforce development and training. Finally, some key points. We did have some divergent opinions on the relative importance of data-driven approaches and purely data-driven approaches and process-based models. And I think for a large part, those are partly due to focus on the different classes of applications that I mentioned at the beginning. It's one thing to use a data-driven model in a streamflow projection or a streamflow forecasting in the current climate. It's quite another to a different class of applications to really try to understand the evolution of the water cycle and how it will interact with the carbon cycle in the future. We can't really observe many of the hydrological processes we're interested in. Groundwater, soil water, very difficult to observe. Making it really difficult to rely on machine learning alone. So I think there was a consensus that process models will really continue to be important for Earth system prediction. This is probably obvious, but the hydrological system is changing. And so it's important when we deal with data-driven approaches to be very mindful of that non-stationarity and even threshold behavior where you might get a completely different type of system if, for example, a fire or a vegetation change. I think there was a lot of discussion about data. Data is an issue. I think we really don't have the kind of data that we would like to really deploy machine learning. There are caches of existing data that haven't been exploited yet, we feel, but there is maybe a need for additional data collection, probably in the area of getting better data for ground truthing, remote sensing data, and that's a traditional strength of this program. And so that kind of wraps up our high-level overview.
Great, thank you, Scott. I have lots of questions, but I will hold them. All right, Mavrik, would you mind going next?
Oops, let me unmute myself and then I can say, sure, I will.
Can hear you.
Okay, let me pull my screen.
And then we'll go to Christa and then Charu.
Okay, and let me see if I go, is that working?
We can see it.
Okay, so first of all, I will apologize. I was on travel most of last week and had some computer issues, so we didn't get through to summarizing the Watershed Science session, but I'll do my best to walk you through some of these slides. So the co-chairs for the Watershed Science session were myself, Carl Stiefel, David Moulton, Xiuan Chen, Scott Painter, Dipankar, Dwivedi, and Lili. And we started off by reminding the invited participants, something that Gary has been mentioning every in our breakouts, that to think relatively, to think big, and think of this as an opportunity to fundamentally change how DOE pursues modeling, observation, and computing of watersheds, right? So to try and think at a large scale how machine learning may be applied in the short term and the long term. We had initially a kickoff session. We had 4 invited speakers. Praveen Kumar talked about causal machine learning in the context of watershed processes. Lili talked about deep learning for hydrobiogeochemical processes. Alan Liao presented his work on on-demand machine learning as a strategy to speed up reactive transport simulations. And Tianfang Su talked about inferring precipitation discharge dynamics in complex karst watershed systems using hybrid physics. We then followed up with pre-recorded 1-minute presentations for 7 of the 8 white papers that were part of our session, and I won't go through all the titles. And then after those 1-minute presentations, we broke into 6 breakout sessions. I think there was about 85 participants, but I wasn't watching the counter very carefully. And the six breakouts included co-design, data collection and assimilation, hybrid AI models, which included on-demand machine learning for reactive transport, AI application to extreme and future effects and events, watershed microbial dynamics and ecology, impacts and feedbacks to human and engineered systems, and strategies of scaling. Each of those breakout sessions focused primarily on the 5 charge questions that was provided by the AI4ESP core team, although those questions were adjusted a bit for each of the specific topics within each breakout session. As I mentioned, I didn't have too much time to synthesize the data, but I pulled some of the key topics and themes that that came out of many of these breakouts, and I'll walk you through this relatively quickly. There was a lot of discussion about data, various aspects of sensor development, sensor deployment, data assimilation, harmonization, curation, access. There was an interesting discussion on development of a data-centered community of practice and high-density observatories as training data sets for defining processes. And in general, a lot of discussion about this issue of sparse and scarce data on the one hand, and high density data that's available. So this juxtaposition of scarce data in the subsurface and high density hydrometeorological and sensor data, and how do you link those two and learn from high density data something about the subsurface in which you're inevitably going to have data scarcity. A lot of discussion about the value of physics-informed machine learning, issues of interpolation versus extrapolation, what the predictive capability of physics-informed ML might provide us, how it would be employed in issues of ecosystem adaptation or extreme events where we're getting into events that may not be as easily interpolated based on the data sets that we have. We had a whole session on on-demand machine learning, which is based on the work from Alan Leal, Seems like a really promising application of ML for speeding up reactive transport modeling, but there still remain a lot of questions on how those might be applied for chemical kinetics, complex physics and hydrology, and in particular microbial reaction networks, and how that might, those on-demand machine learning might be employed in that area. A lot of discussion in ecology in terms of ML being really a nascent area for ecological studies. How do we employ machine learning in interactions at the soil plant microbe scales, and discussions on how we might link trait-based emulation of microbial system ecology. And an interesting thought about whether we need something like an Ameriflux for subsurface biogeochemical networks. In terms of human engineered impacts, there was discussion on incorporation of land management practices. How do we deal with prescribed burns and erosion, ash, aerosol biogeochemistry, and in particular, how we might incorporate human decision-making into model prediction. There was also some discussion on data access from various agencies, both the government agencies and industry, and how we might resolve data access issues. Finally, in terms of scaling, there was discussion on capturing effects of small biogeochemical active zones, interfaces, predicting emergent biogeochemical function into continuum scale models. Lots of discussion of surrogate models, multi-fidelity models, whether machine learning can be used to relate low fidelity models and higher fidelity process models, and how that might work. And I think something that Scott already mentioned, this idea of having a software infrastructure in place to make it easier to experiment with combinations of machine learning and process-based models. And that's my very quick summary.
Wonderful. Yes, it's very quick, very short. All right, Christa, do you want to jump in?
Sure, thank you. Yeah, so I'm Christa Brelsford, reporting from the Human Systems and Dynamics section. Thanks also to my co-chairs. So the way that we started characterizing the grand challenges for understanding the incorporation of human systems and dynamics into Earth system predictability are, on the one hand, thinking about primary drivers of humans on the Earth system. So essentially the goal here, the need here, is to reduce our uncertainty around aggregate greenhouse gas equivalent emissions. Then there are also a suite of major grand challenges around the secondary drivers of anthropogenic influences on the Earth system. So a handful of examples are thinking about the effect of coastal infrastructure on ocean dynamics, thinking about the effect of land use change on emissions, thinking about chemical use on sort of global biogeochemistry, for example, fertilizers and plastics, thinking about the effect of land use on ecosystem processes, and then urban heat island on atmospheric effects. Then we can think in the other direction about the effect of the Earth system on humans. And so the big grand challenge here is making models of the Earth system processes usable for decision makers. And so a handful of examples here are thinking about, basin scale hydrological predictions can then inform infrastructure planning, agricultural investment, or optimize the allocation of protected spaces. And then another sort of downscaling climate models to a human relevant scale, human scale statistical characteristics on all of the climate hazards, wildfires, wind, heat, cold, snow, and ice. All of this is useful for understanding impacts of Earth system processes on humans, and could be used to inform things like building codes or land use planning. And then finally, in all of these contexts, understanding the coupled feedbacks between anthropogenic activities and the human Earth system. This is a grand challenge because it really hasn't been incorporated very much so far. Then thinking about the next sort of set of questions we were charged with were generally summarized as what comes next. And so all of our 6 breakouts had long discussions on the challenges associated with data. Data around human systems is currently mostly privately owned, it's proprietary, and there are a lot of legitimate commercial privacy and ethics concerns in these data. And so one of the things that in order to do human Earth system prediction, we need to address these data concerns. If we don't, almost any computational work at the intersection of humans and Earth system predictions, we think is fragmented, piecemeal, and ultimately it's not scalable. So this data challenge, all of the sort of computational infrastructure that we heard about from Scott and Mavrik are important, and also dealing with the concerns of data ownership and privacy are a unique and a specific challenge to the human sector. Then additionally, many of our breakout groups discussed the challenge of workforce development, that we need socialization between domain scientists, especially social scientists and computational methodological scientists. And then finally, in the human system space, humans are interesting because we have stakeholders. And so addressing the stakeholder engagement problem is also an important step in creating our ability to do interesting science at the intersection of human systems and Earth system predictability. So the methodological, and then sort of thinking about our next steps from a methodological perspective. A handful of challenges are around, as we said, data processing and management infrastructure. So one example here is that there are a lot of historical and textual data that haven't yet been digitized or put into a form that's accessible for research. So natural language processing is a useful strategy for that. There's quite a lot of existing research that's important, using things like convolutional neural networks to interpret information from remote sensed imagery so that we can make inferences on, for example, where human settlements are in the present or have been in the recent past. Then finally, a big set of work is thinking about how we represent human Earth systems. So for example, long and short-term memory-based research based on recurrent neural networks can be used to represent regional and Earth and human system dynamic processes. We can use there's a potential of using unsupervised methods to identify what information is critical and decision relevant in these human contexts. Agent-based models, we think, are a really excellent opportunity for a bridge between data and simulation strategies. And then finally, emulators are an option for fast, cheap, and flexible modeling, coupling, and exploration of feedbacks between human and Earth systems. Again, with the overall theme that the representation of humans in Earth system models is so far really still nascent. So there are a lot of strategies that need to be tried and that there hasn't been a lot of exploration in this space so far. So machine learning is an absolutely important strategy, and we just sort of have to start somewhere. And then finally, model explainability and credibility is obviously important for all of this research, and particularly in a human context. If we're going to present models of interactions between the human Earth system to people who might actually use them to make decisions, those decision makers should believe that the model accurately represents the processes that are important for their system. That's all. Thank you.
Thank you, Christa. And I think everybody in the audience and all of us, we got to start somewhere. We believe this can do some good, but we really need to figure out where we're going. So thank you very much. Charu, are you ready? Let you go next.
We already presented for hydrology, and Scott did that. So
oh, that's right. I'm sorry. Okay, wait, who did I miss? I'm missing one. I think, am I? Assist anyone?
Neural networks.
Oh yes, please. Sorry about that. And who's going to present for neural networks? I don't know if I have a note on anyone that was not going to. Auroop, are you around? Are you on? You may be on the wrong side. Tracy, will you guys look for Auroop? He may be on the wrong side of this one. And I apologize, I didn't see that earlier. While we're looking for Auroop, I'm just going to do a quick reminder. I want to thank everybody for the last day we had in reiterating our code of conduct, how we feel about that, how DOE feels about that. Please be respectful of everyone, regardless. Be professional, keep the discussions to the topics, don't make things personal, and be very respectful when you're doing that. I think, are bringing together so many people from so many different backgrounds. There's so many things that we don't fully understand to a critical degree. Be careful when you're talking to each other and recognize that we know we don't understand all the other sides and all the other aspects, and there's no way anyone could possibly understand that in this space. So please just keep it as professional and courteous and polite as you can. And if there are issues, we will take actions as we noted last week, but I expect going forward, we will not need to do that. It doesn't appear that Auroop is on. Is anyone from the neural network session able to kind of get, even if you don't have slides, could just give us a real quick high level rundown? And you could put something in the chat or Q&A. I see something I haven't seen in there. Okay, there's a question in the Q&A for the hydrology group. Okay, well, I did not think about this happening, to be honest, so I'm not quite prepared. But in that case, I think we will have to move forward. And what we can do is go ahead and take our break just a little bit earlier. I think we can keep on time, but since we're taking the break early, please try to come back just a little bit early and be prepared to start the next session straight away. And let's see, I think that's everyone. We'll see you on the invited session in a moment. And did we capture that question? We did, an answer, okay. We can put that, oh, that was just a confirmation that we addressed those. All right, see you all in a bit.